Okay, welcome back to the second video. So as we noticed, we are able to write the sequence as a function and then take the limit if we need to. That is not always required. So notice that the properties of limits of sequences agree with the properties for limits of functions, as you can see in the box below. So I have two problems that I would like to try. So pause the video and see if you can find, once again, the limit of these two sequences. So once again, in this particular case, I'm interested in finding the limit of a sub n as n goes to infinity. So it certainly looks like we're going to need to divide by something. So because we're interested in not having the issue of a 0 in the denominator, what we'll do here is we'll divide the top and bottom by n squared. So I'm going to divide the top and bottom by n squared. Okay. If I do that, I'm left with 1 over n squared minus n cubed divided by n squared. On the denominator, I have 70 divided by n squared, and I have a 4. All right, let me go ahead and simplify this a bit. So as I take the limit as n goes to infinity, I notice that 1 over n squared, that goes to 0. 70 divided by n squared, that goes to 0. My minus n here actually goes to negative infinity. Let me rewrite that better. So I have negative infinity on the top and I have negative 4 on the bottom. So that's still infinity. So unfortunately, this particular sequence diverges. Okay, for the second problem, once again, we want to take the limit as n goes to infinity of the sequence 3 to the n divided by n cubed. Now, if we test first by taking the limit as n goes to infinity, we realize that the top goes to infinity and the bottom goes to infinity. But wait a minute, we recognize this as an indeterminate form, and we're going to require L'Hopital's rule here. So we're going to try to do this. Take the derivative of the top independently from the derivative of the bottom, and then reevaluate the limit. Looks like we're going to need a side note to be able to figure out the derivative of the numerator. So what we'll do is we'll let y equals 3 to the n. We'll take the natural log of both sides, which gives me n times the natural log of 3. And now we'll take the derivative, implicitly of course. If I do that, I'm left with 1 over y times the derivative of y. And on this side, on the right side, I'm just left with natural log of 3. If I now multiply both sides by y, I'm left with y prime is equal to y times the natural log of 3, making the original substitution. Now I know that y prime is the natural log of 3 multiplied by 3 to the n. All right, so let's go back and try that. So that means that I have the limit as n goes to infinity of the natural log of 3 times 3 to the n power divided by the derivative of n cubed, which is 3n squared. Now, let's try it again. I see that I have, once again, another indeterminate form. That means more L'Hopital rule. So I'm going to take the derivative once again of the numerator and independently of the denominator. The denominator just gives me, let's see, 6n. In the numerator, I'm going to follow the same side note again for the derivative of 3 to the n. So that's just going to introduce a second natural log of 3. So I really have the natural log of 3 squared times 3 to the n power. And if I now evaluate the limit, I realize that I am still in trouble, and I'm going to need the L'Hopital's rule one more time. Here we go. So if I take the derivative of the numerator one more time, I introduce yet another natural log of 3. So I'm up to 3 of them. So now I have natural log of 3 cubed multiplied by 3 to the n power. And on the bottom, the derivative of 6n is just 6. We can do this now. Unfortunately, as we take the limit, the denominator stays fixed, but unfortunately the numerator goes off to infinity. So this particular limit is infinity, which means that, once again, this sequence diverges. Okay. Sometimes a sequence happens to lie between two other sequences. So take a look at the picture below. The terms of sequence B sub n are sandwiched between those of the sequence A sub n and C sub n, forcing them to the same common limit if all three happen to converge. This is once again the sandwich theorem for sequences this time. So if I have a sequence A sub n, B sub n, and C sub n, and they're all sequences of real numbers, if A sub n is less than or equal to B sub n, which is less than or equal to C sub n, if the limit as n goes to infinity of A sub n and C sub n is equal to L, then because B sub n is stuck between A sub n and C sub n, the limit as n goes to infinity of B sub n is also equal to L. Let's take a look at the example below. So we have the sequence A sub n is equal to sine square of n divided by 2 to the n. Well, let's take a look at a couple of things. So for n greater than 1, one of the things we know is that the sine square n divided by 2 to the n is greater than 0. All these are positive numbers. The other thing that we know, or we can conjecture actually, is that sine square of n divided by 2 to the n must be less than something. We need to be able to find something in between. And so I'm going to conjecture that it's less than 1 divided by 2 to the n. Let's take a look at a picture. Notice in the picture that while sine square x divided by 2 to the x oscillates, it oscillates below the function 1 divided by 2 to the x. So we can make that kind of determination that one is always less than the other as x goes off to infinity. So note that really sine square n divided by 2 to the n is sandwiched between 0 and 1 over 2 to the n. And since we know that both 0 and 1 over 2 to the n converge to 0 as n goes to infinity, sine square n divided by 2 to the n must also converge to 0.